So next we will be talking about subnetting. Now keep in mind you can't have IP addressing without subnetting. And this goes for IPv4 and IPv6. So I'll come over here. You need to know that IP subnetting works pretty much the same way as IP addressing does. 4 octets, 256 possibilities, and 0 through 255. Except here we were determining the difference between 2 IP addresses being on the same network or different networks. When we get to IP routing, we'll discuss in great detail how to accomplish the routing between these networks and subnets, but first you really need to know how to create the subnets. So as we showed you earlier, here is the table again. You use each bit to determine the addition or subtraction depending on which way you're going. From 128 down to 0, this gives you potential masks of 128, 192, 224, 240, 248, 252, 254, and 255, depending on what network that IP address exists on. So this table represents how subnetting is going to be calculated. We will have to figure out which side of the IP address is the network side, so if 2 hosts are in the same network they can communicate without the need of a layer 3 router or layer 3 switch. So say we have 2 IP addresses. Now based on our class C, you might say 192.168.0.1 and 192.168.1.1 are on the same network, and you would be correct if that was the case. Based on the 192.168/16 or the 255.255.0.0, they would be on the same network and not require a layer 3 device to communicate. So here is a good example of how we calculate which network lives on which network. So 192.168, you're going to see have 255, 255. Anything that does not have a bit associated with it is going to be our host side. And you're going to notice they both, with a /16, are on the same network, but of course are different hosts. This host is 1.1, this host is 0.1. Now if we change it up a little bit, we're going to give them a new custom subnet mask. 192.168.0.1 with a /24 and 192.168.1.1 with a /24. Now these IP addresses will not be on the same network and will need a layer 3 device to allow them to communicate. So if you look here, we have 3 octets that are 255. This tells us that the 192.168.0 is a network and the 192.168.1 is a network. So now they're on different networks and they have their own host ID of 1. So for these to be able to communicate, we'll have to have a device in between them. So if we have 192.168.0.1, we will have to have a layer 3 router or switch that has access to each of these networks to allow them to communicate. Now when we get into introduction to networking, you're going to notice that the destination MAC address for this host here is actually going to be the physical interface, or SVI, on the switch or router, which will change and forward that destination MAC to reach the second host. You'll see here that all of the bits from the first 3 octet are used. 8 ones, 8 ones, and 8 ones, which gets us our /24. 8 plus 8 is 16, plus 8 is 24. This tells you that the first 3 octets are not equal, they are in different networks, as you saw before. 192.168.0, 192.168.1, different networks. On to more of a tricky part when we talk about advanced subnetting. So in getting away from this thought of classful network addresses, we come to what's called classless. And we talked about CIDR before. Classless interdomain routing is where this notation comes into play, and you have to be aware of the bit counting within a subnet mask. As an example here, we have 192.168.0.0, however, it is a /28. This is an example of CIDR notation rather than spelling it out. 255.255.255.240, 8 plus 8 plus 8 plus 4 equals that 28. Now here is a really nice table that allows us to see where the octets live and what is their bit notation, as well as the subnet mask identifier. So for example, we're seeing here with a /28. Looking at our table, you'll notice that we are in the 4th octet. This tells you that any address in the 1st, 2nd, or 3rd octet that is the same are on the same network. However, how do you tell from the 4th octet if the device is on the same network? So one of the easiest ways to do that is counting. You'll see here that a /28 ends in 240, as we see here. What we can do is we can take 256 minus that 240, and it gives us 16. So moving down a little bit, we're going to talk about what this /28 provides for us. So a /28 is 240, the 4th octet. We have 240 here. Because you understand the math, the /28 is 256 minus 240. So every 16 addresses in the 4th octet is a new network. Here's a nice little flow of all of the IP addresses that are in different networks. So you'll see here, because we have a class C IP address, it starts with the 192.168 and doesn't change all the way down. But you'll notice the 3rd and 4th octets can be changed. And using our subnet masks, you'll see here that we have a whole lot of potential networks available to us. So you'll see here 192.168.0.0, 0.16, 32, 48, 64, 80, 96, 112, 128, all the way down to 1.0, 1.16, to 240.0, all the way to 255.240. These are all the potential networks you can have, and then some. Because you're going to notice I have 256 possibilities in the 3rd octet for my subnet. Plus, of course, all of the networks in the 4th octet. Based on the calculations above, we can deduce, of course, that every 16 in the 4th is a new network, and RFC 1918 states private address space is between 192.168.0.0 and 192.168.255.255. We also have the ability to do a little bit more math here. So we'll see here that 256 times 256 is 65,536. If we divide this by the 16 we saw earlier, it gives us a total of 4,096 potential networks. Because we have these 12 network bits to choose from, keep in mind Class C has 16 bits we cannot change, we can count the bits available. So we have a /28 minus the 16 for a Class C, and this gives us 12 bits. We can do 2 to the 12th power, which also equals 4096. Once again, based on our calculations, we have 4,096 networks as a maximum using 192.168.0.0/28. Now keep in mind, this can be done with any of the octets you are working with, but you need to remember RFC 1918. 10.0.0.0 through 10.255.255.255, 172.16.0.0 to 172.31.255.255, and 192.168.0.0 through 192.168.255.255. Now I'm going to take us back up to our table here, because I really want you to remember this. This is something that I use every day when I'm dealing with subnet masks. If someone comes in and tells me a particular IP address and CIDR or subnet mask, I can tell right away where it is, and what the networks are. Now, we will talk about this more in depth in the network versus hosts. However, it's just one of those things that I can't stress enough. RFC 1918 and the subnetting. Which octet is it in? And which bit notation or CIDR is it in? So if someone tells you it's a /30, you'll know that it's a 252. From 252, you'll notice that there's 4 addresses available. If you come over here and do a /9, you'll know that that is a 128 in the second octet. By doing the 128, you'll notice that it's every 128 in the second octet that gives you a new network. So we'll take this as an example. So 10.0.0.0 with a /9. So you'll see here in the second octet it changes. The first octet does not change, and we use a single bit. So we have 10.0.0.0 and 10.128.0.0. These are the only 2 networks we're going to have with a /9 in the Class A network range. I know that was super simplified, but I wanted to make it easy and give you a good understanding of where the last bit lands is the octet that changes based on our subtraction. Every 32, every 16, every 8, 4, 2, 1, 64, 128. So in the next video, we're going to be talking about the networking and hosts. I will have that video out for client versus network in the next video. Hope you can stay tuned for that. Thank you for watching.